to start today's program with Jesper Andersen, who's going to talk about GraphQL.
Okay, thank you, Alex. Yeah, so this talk is about this query language called GraphQL that I've been working on at work for the last 2 months, I guess, 2.5 months. So now I feel I'm kind of ready to present what it is all about and know what. I mean, I'm going to try to give you an idea of what it is and how it works and all that stuff. I hope you can read the slides. So my glass is not really good at reading from a long distance, but I hope your eyes are better than mine. So yes. So what I'm going to do is I'm going to do a 2-stage process here. I'm going to give an overview of GraphQL itself, and then I'm going to dig into how you would, implement a GraphQL implementation on the server end if you want to do that at some point, and how you can approach it. My approach is a bit different from what they normally do, but I think I have a better approach. So, yes. There's a disclaimer here. I'm only giving the introduction here. GraphQL is a pretty big language, and I cannot really cover everything, so I have deliberately skipped a lot of the concepts in it, and then what I want to try to do is to give you a feel for how it works and how it operates, and not really go into details for some of the more subtle things. Also, they are continuously extending the spec they have on the language, so it's evolving as we speak, essentially. So things are changing. The things that work are kind of set in stone, but new things are getting added all the time. So what is this about? Well, it's created by Facebook in 2012, internally. And then they released a public draft spec of this last year. Internally, they use it presumably on Android, iOS, and on the web in order to make a way for clients to query the server side. And they have almost replaced their internal APIs with this GraphQL API. For a lot of the things that they're doing. The thing you can use it for is basically to get rid of REST in your application stack. Because it puts itself right on top of REST and then kind of takes over the REST stack. So you have one REST endpoint in your system. So your router has only one entry point, essentially, and that is enough. The way it works is that it is a client-server query language, so the client makes queries to the server responds with answers back to the client. Lately there's been extensions where they're trying to add, say, streaming capabilities, subscription capabilities, batch requests and stuff like that, but I'm not going to cover it. Just know that they have a solution for this if you need a streaming, a streaming endpoint for something. Also, it's not really tied to the web service in the sense that it is not tied to HTTP. You could use it for over WebSockets. You could use it over protobufs in principle. So the transport layer you use is actually up to you. This is just the thing you put on top. The way it works is, it's a wrong approximation, but one approximation you could use is that it is SQL for the web, in the sense that the client declares a query, and the query is sent to the server. The server tries to resolve that query and then give back its answer. And there is a concept of a schema in this which defines what are the valid queries. And the schema defines essentially what your server supports. So this corresponds to the endpoints in a RESTful web service. There's only one endpoint, but there's a schema definition inside it that defines what you can query for. So essentially what you have is kind of like SQL for the web, because the client can now evolve and change its queries without the server changing. And that is the basic idea here, that we want to have that capability. Here's the first example, and I hope it's readable. So what you see on the left side is what you actually input as a GraphQL query, and what you see on the right side here is the output. And it's not really tied to JSON, but the default is that you get JSON out. What you see is we have a query over here, and the query is called Q. You can name queries because if you have multiple queries, you might want to refer to one query over the other. Then we have a query here where we say we want a field called monster, and we have an argument, an ID for the particular monster we want. And then what we have in the brackets are the fields inside the monster object we want. In this case, we want the identity of the monster object, and we want the name of it. And what we get out is an identity, which is essentially a base 64 encoding of an internal structure, in this case, and a name. In this case, the particular monster we're looking at is a goblin. It's very important that clients are forced to say exactly what fields they want. There's no kind of like in SQL where you have a star query where you can say, give me everything in this object. That is non-existent in GraphQL for good reason, because if you have that, then it's hard to extend things in the future. So we force every client to say exactly what it wants. And also note that the output structure and the input structure, that is the query structure and the output, matches each other. And this is a deliberate move, and I think it's really good. So the JSON will always reflect what the query looks like. Here is the a bit more involved example. So here we are asking for a room. It has an identity. And now the room has exits, which has multiplicity. So what we get out is that for each exit, we want its direction. That is presumably in what direction that exit is moving. And then we want the room behind that exit. So now this is where the name GraphQL comes into play, because it's now a hierarchical query on presumably a graph. It doesn't have to be a graph, but it looks a bit like it. So here we are going, say, give me the exits in the room, and for each exit, give me the direction, and give me another room. And that room, I want the identity and its description, right? So what I get is that the room I'm looking at right now, the top room, is, I mean, it has, it's the dungeon entrance, and then you get all the exits. And for each exit, you get the direction, and it's, and inside there, you get a room, and the room has a description and an identity. And note that the thing here is actually wrong. So that's a miscopy by me, because over here, I'm not asking on the topmost room, I'm not asking for the description. So I made a mistake here in copying the thing. So just the thing I've marked here, expect that to not be there. Now, there's some important concepts here. A schema defines that a field can be either a scalar thing or an object. So if it's an object, it's just a product of multiple objects or scalars. If it's a scalar, it's just, you know, a thing by itself, like a date or a color or a string or something like that. The schema also defines where if a field is composite, that is, if it's an array of things. This is the case for exits in this example. And it defines if a thing is not null. So you can have fields that are supposed to be there, and you can have fields that have nullability, so they can be null if you ask for them. So the main points about this system, and I might skim over some of this because I might have said it. The thing is that it's a hierarchy query, so you are essentially querying an object inside the graph, and then you are saying, for that object, I want to walk over here, and for there, I want to walk over here, and so on and so forth. So you are essentially building your query is essentially building a path in the graph that you want to grab. So look at it as if you had a schema that defines a virtual graph of your system, and then you essentially do a query in a subset of that graph. So you're kind of spreading out from an initial point in the graph and getting all the data back. That is essentially how it works. It's very important that in this system, the front end is actually the driver of the query, meaning that it enables product-centric applications. The thing is that if you have a client and the guy at the client wants to say change something or want to make a smaller change, chances are that you don't have to do any code on the server side. If it's a new field, you just add the field. If you don't need a field, you just remove it. If you want to grab some new data, you just grab it. If it's possible to grab inside the graph, so it allows you to actually, in a certain sense, build front-end applications much quicker. Because once the back-end things start, you know, falling into place, then the front ends are actually freed up to just do the queries they want freely. Another important thing is that the input language is completely type-checked. So that means if you do a query that turns out to be invalid, then it will be rejected. And the response is type-checked as well. So if the server does the same thing and returns something that is invalid, then the contract checker will say that that's not a good thing. So essentially what GraphQL also provides is a contract between the client and the server. And you don't have this in typical RESTful web services where you have JSON. There you're just giving blobs back, but you don't know what to expect in principle. And there's no place it's documented. Here, the types in the schema will actually document what you can query inside the system. So that, in my experience, that has turned out to be very, very powerful. Then there's some more points. The server will guard against bad queries. So it has certain validation steps it'll do. So if you do a query that is completely whacked, it'll tell you that this is probably a bad query to make, because it's likely that it'll be very wrong. And if you have very complicated queries, that helps a lot, because now you're being guided on the way to actually build your query the right way. It's also introspective in the sense that the client can actually request the schema from the server and request documentation as well. So if you have, in RESTful services, if you have used something like Swagger or something like that to embed documentation into your server endpoints, well, it's built into GraphQL. You don't have to do that. You just have to add it to the schema. And then, as I said, one of the main points is that you have backwards and forwards compatibility in this system. You can deprecate fields from the schema you don't like anymore, but clients can still request them even though they're deprecated. And you can add new fields to the schema, add new objects to the schema while you're working and extending your system. And the clients that don't know about that, well, they'll not get that data because they're not part of their queries. So this allows you to kind of like go into the server, extend the server somewhere with new data, deploy that into production, but no client is using it yet, so it's fine. And then as clients start, grabbing these things, then you can start using them as you see fit. So there's something where it's not very RESTful. For instance, there's one query, and then all the operations you want to do runs on the server side. So imagine that you had a normal service where you have your client, you do a request, you get back a response, you do another request, you get back a response, and now the latency between your client and the server is summed up every time. It's additive, right? Here what you do is you make one query to the server. The server does a lot of queries down here, presumably with very low latency, and then you get one response back. And that usually means that you get lower latency queries in this system. Because what normally you would say, okay, give me a list of products in this system, and then for each product, list that product. And that would be 1 + n queries. Here you can do it in 1. And then people say, okay, fine, so now I'm going to add my special REST endpoint that does this on the server side. But that's boilerplate code. You just added more code on the server side that you don't have to add. In GraphQL, the advantage is that this looping you're writing when you're doing your kind of composite 1 + n query on the server side is built into the execution engine of GraphQL. So that means you only have to worry about how do I dig out a single object. So essentially the idea is that you have a story for this, and you also have a story for how to use caching in this and do batch operations on the back end. So you can go do one grab on the database as well in the back end. And this even further lowers the query latency in the system. I'm going to talk a bit about perhaps one of the most powerful things of GraphQL now, which is the concept of a fragment. So if you look at this query I had up here, you can see that there's a lot of things in it, and it's complicated. And what you often want to do is you want to kind of excise the fields you want from a given object. And the way you do that is by using these fragments. So let me move down to that. The concept here is that we have this monster fragment we have declared here. And it says the monster fragment is on the object type monster. And it requires, or it requests the identity, the name, and the hit points of that given monster. So now when you have a query like this one, you can just refer to that monster frag. and it expands into the fields that the monster frag contains. So this allows you to kind of like, if you have, in this case, where you use the monster frag in multiple places in the query, you can now move that, factor that out into a separate fragment. So this is one of the important uses of fragments, but they're used for more things in the system, as we'll see. The thing is, as I said, it allows to do concise reference to fields, so you avoid having to repeat yourself all the time. But it also provides essentially downcasting, in the sense that in this room query here, where we have some contents, the contents are not necessarily a monster, because the room might contain, say, treasure, or it might contain other things like player characters and stuff. But this actually says that in this room, if there's contents in there, and the contents happens to be a monster, then output it. Otherwise, skip it. So the fragment here also works as kind of a selector that can select among multiple types and say, I'm only interested in this if it's in particular a monster. And the reason that's powerful is because suppose that I had a client that didn't know about, say, treasure in rooms yet, but knew about monsters. Well, if the client uses this particular query and we later on add treasures into the room and the concept of treasures into the system, well, this particular client doesn't know about it, so it won't get them. So this is where you begin to have this ability to do, backwards and forwards compatibility in your API, without having to go back and change the existing clients. And if you have ever tried to get applications through on iOS and Android and if you know how long the uptake of upgrading for people happens to be, then you know that once you have put something out there, it'll never ever go away. I mean, there's always some client somewhere that is using one of the older versions of your API, right? But the idea here is that you can build it into the system. And there's an anecdote from Facebook. They did this in 2012, and they claim that they haven't had to actually make a major change that is not backwards compatible yet, which is a pretty impressive claim given that it's Facebook. I mean, their graph is big, I guess. So the idea here is that this is also used, not only is it used in order to factor out commonalities in your queries, but it is also used in order to kind of pick out stuff in the graph. The way it works is that you have, so as I said, graphs primarily contains two things. It contains something called an objects, and it contains scalars inside objects. So objects either contains objects or other scalars. But in the schema, we have different things we can define in order to make things easier for us. And specifically, what we want to try to have is a way to do heterogeneous queries in the system. So what if I have, in this example here, where I have my contents, and the problem is that it can be monsters or treasures or players or different kind of things. So this is not homogeneous, and if you have a normal type system, the problem is the contents would only be a single thing. So we need some way in the type system to be able to say, well, this contents can be different kinds of things at the same time. And this is where the concept of interfaces and unions in the language crops up. So the idea is that an interface defines and says, okay, so I have that object type and that object type and that object type, but they all have these fields in common. So they all kind of implement this interface. It is not a subtyping hierarchy, so it's not inheritance. It's just interface implementation. And what you use it for is to kind of like pick out something that is common to a lot of things. So for instance, both non-player characters, player characters, and monsters might have hit points in common, say. They might all have hit points. And hence, it might make sense to kind of extract that notion of something that can battle against each other into an interface. So you could have an interface called a combatant, say, that you then use when you have two things competing against each other inside this dungeon that we're building up here. So this is what you would use interfaces for. And then there's unions, which are that I just have a bunch of objects and they have no fields in common. So if you're a type theorist, this is kind of like a sum type, but not precisely a sum type. There is a tag, but it's kind of hidden. So this allows you to do, say, you have something that has nothing in common with everything else, which is the case in the room. I mean, when we're looking at the contents here in the room, we might say, well, it's okay that there's monsters in there, but monsters have nothing in common with, say, treasure. So they have no fields in common. Perhaps they have an identity in common, so there might be some kind of node object that they both implement, but otherwise they have nothing in common. So we can get away with that by saying, well, the contents here are just a thing, and things are union of, say, monsters and player characters and treasure and whatever you can have in your room, right? So this is the way you kind of like get to do heterogeneous things in the query. And interestingly, SQL doesn't really have this, which is one of the reasons why it's hard to do these kinds of things in SQL. If you've ever tried doing essentially a sum in SQL where things can be either that or that, you get into trouble. And there are 4 ways you can solve it, and all of them have disadvantages that are really hurtful. So one of the specifics that they tried to solve when they built GraphQL was that they needed a story for handling these kind of heterogeneous queries, because they're happening all the time in practice. It's very often that you have something of one type and something of another type, and they can commingle inside the system. Yet our older systems have had no way to handle that, which is kind of weak. So they have built that in. Then you get to where it becomes, now we kind of like add another layer. So when you have a query queue, it can take parameters. So here we have a query like before on the monster we asked for its fragment. And now this part here says, well, the particular ID that we are going to supply is coming from the outside. So now it's essentially a function. Our query is now a function over the identity which we provide. And then the query will run, and down here, when before we had a string here, now we have the variable reference to our parameter from up here. So now we can reuse Q to query different kinds of monsters. And of course, we can add more and more. It's like a function. We just add more and more parameters into it. Note that the exclamation mark here says that this is a non-nullable value, meaning that you have to supply it. It's not allowed to not supply a monster ID to this query. That would be a mistake. So what you usually end up with is that you end up with a query document for your whole application, one query document, and it contains like 60 or 100, maybe 200 different queries, and they're all parameterized like this. And then when you actually do your query, you say, well, I want that query document, and you have a unique reference for that query document. I want that query inside it, and then I want these parameters going into that query, and back you get the answer, right? And this is where you start seeing where the security in the system is. Because what you do in your staging environment is that you build up this query document, and you take its checksum, and now you say when it's in production, you cannot change it, because you lock it down by that checksum. So what happens is, once you are in production, you can only do the queries that you pre-declared in your staging environment that are allowed. So even though you have all this power when you're developing the system, you have none of this power when you're actually running. And this is a security trade-off we want, right? We want to have the freedom to build new stuff quickly, but then we need a lockdown once we hit production. There's also another very good argument here, which is that you can use this in order to, the attack vector of the system gets that much smaller when you do this. So arguably it's more safer. How do you change things? Well, there's a concept called a mutation. So in this case, we are mutating, we are adding a new monster by calling a helper here. We are essentially calling the function introduce monster, and it takes an input object here, which is then looking a bit like a JSON thing. So here we are actually adding a succubus with 24 hit points, and I think it's purple. And And what you get back then is that then we have a rule here that the client mutation ID is just reflected, so we can see that it's this particular client from the or this particular mutation from the client side. And then we ask for the ID and name, and out comes the monster here, and it gets a new ID that was just generated for us. So this is how you do mutations. They look a lot like queries, and internally they're implemented exactly like queries, except for one thing, they're not parallelizable. Of course, when you're doing multiple mutations, which you could by adding yet another introduced monster below this one, then they run in series, because otherwise you would have race conditions. But otherwise, they are exactly like a query. So what you've seen until now is that I'm kind of building up a dungeon schema here as a small. It's actually one of my test cases that I just, added more stuff to. So it's funnier to work with. There's a GraphQL server running in the backend written in Erlang for this that I wrote from scratch because there were no thing. And the dungeon itself is actually backed by the Misha database in Erlang, just to make the point that it doesn't necessarily have to be a graph database that backs it. This is just a standard. It's not a SQL database, but the schema is essentially SQL-like. So that is another way of doing it. I have a demo time, and now it's famous last words because it might fail. So this is actually the interface you have to GraphQL if you start working with it. So what happens is that in JavaScript, they build a complete interface to this thing, where they use the introspection features of the underlying GraphQL server instance you are pointing to and grabbing out all the data. So this is interactive. If you go over here, you can get the documentation. You can look at the schema. You can ask for what is the possible queries. You can say, well, we can query for monsters and rooms, and it's typed, right? If we pick one here, we get in, and we can look down and see what monster ID to retrieve. We get back a monster. And here I haven't really documented them, but that's the idea. So if we go in here, you can say how many hit points does this monster have, and so on. So you have this ability to automatically get documentation for your API. But this query interface uses it for more things like that, just that, because if we go here and we start adding, say, a query, it does auto-completion. So if I say I want a query here, and I ask here what can I get, it starts auto-completing on the introspection thing, right? So if we want say a monster here, just to take an example, and now I don't have an ID, but who cares? Let me just add some ID. So now we are in monster, we can ask what are the possible types there, right? So we might want, so HP here is actually a deprecated field for hit points. So this is an example of moving ahead. So we wanted hit points. We might want its inventory. Okay, so what are the possible things in here? Well, now there's two ways you can define fragments. One is that you can give them a name, but you can also do fragments inline. So you can say it like this. Okay, so these things are possible here, right? So the inventory can presumably contain rooms. That might not be what you want, but in this case it can. So it might be that you have an item in there. Okay, so what are the possibilities of items? Well, I want the name of that item and I want its weight, right? So this is how you build up queries. And I prepared a couple of queries here so you can see examples of how they work. This introduces a new item, right? So I'm trying to add a sort here of some kind that has a certain weight. So if I go up here, you get all the possible things you can run in this query document right now. So we can say, well, run the introduce item query. And then it fails because something is wrong inside my system. So let me just go here and restart it and see if I can get it to work. So there's this thing is running in the background. Let's see if it actually introduces. No, it doesn't. Funny. What did I do wrong? It actually fails because one of my validators fails. It's saying to me that I have two queues defined in this document, and that is not valid. And it also puts a little small squiggly under that one. That might be a hint that something is wrong, right? And there's some of my validators are not entirely done yet, so I'm not really validating them and putting them out yet. I should put over here in the right-hand column that you have two queues. Please fix that. But I'm not right now, so I have to go into the server to figure out what is wrong. Now we remove it, and then we can introduce an item, right? And note that this is a newly generated, the ID here is a newly generated by the Nisha database and given back to us. So this is the idea. Here is an example of a mutation where we add that item into a room, namely this target room here. So if I do add to room, you can see that I now linked that item into that room. And now if I query, I have a room query, if I can find it, over here. So here I'm asking for that particular room, and I'm asking for the contents inside that room. So hopefully, if we do this, we'll get the sort out, which we do, right? So this is an example of me introducing a sort into the world, linking that sort into a particular room's contents, and then querying for it, right? So normally when you are building up your things, you're using this interface to do it. That's the idea. And this is open source and comes for free. So it's within JavaScript, you just tag it on top of your server and you have this ability. The only thing the server needs is to implement the introspection parts. Then this is automatic. So that's pretty neat. And then I'll go further on by talking about the Erlang implementation behind this. So I started looking at other implementations and I thought they were all pretty bad. So I decided to do one myself. Why not? And that's usually where you end up, you know, spending 2 months on something that you shouldn't be spending 2 months on and stuff like that. But when it's part of work, it's okay, right? So I started doing this, and the way, if you look at it, you can look at it as if it is a programming language, right? You have a query language that gets turned into optimized query plans. So the way to address this is to say, well, this is a compiler from GraphQL data into execution plans for a backend. So this is what I did. You write a lexer and a parser, which you do by using the standard lexer generator in Erlang. You could hand roll it, but because we have this thing where we build a query document and then only reference it afterwards, it's not on the critical path, so the speed of this doesn't matter. So pick the thing that is the simplest to do, right? The same with the parser. I use Yak for that. It's not very fast, but it's not on the critical path, so who cares? Then I use a trick from standard ML. So in standard ML, you have no types when you start out and you have the program. So you do a pass that is called elaboration, where you figure out, infer what the types are, and attach them into the structure as you go along. You can do the same here. Given a query, I can look up into the schema and then annotate the types that things have. So now I don't have to go and look up into the schema anymore, because now they are attached to the abstract syntax tree of the thing I'm working with. So essentially, I'm just pulling in the things from the schema I need in order to satisfy the query. And that makes the later stages in the compiler much, much easier, because whenever I need data, it's just in the structure. I don't have to have a separate lookup phase in order to figure out what data I need here, because it has been elaborated into the structure we have. And now the elaborator can also find the first kind of errors, like I have a field that is not even defined in the schema. That can be caught by the elaborator. It's not on the critical path either, so the speed doesn't matter. Then you do a type checker. It's fairly standard, there's no magic in it, just write it. The most advanced stuff is how you type check interfaces and unions, but that's it. If you have done programming language theory and you have done a little bit of this, it kind of writes itself. You have a validator that then further verifies the query document structure. So this is akin to a linter for a programming language. I mean, it's not errors per se, but if you have them in the query, it's very often the case that you have a bug. So for instance, if you refer to a fragment, but there's no way to ever expand that fragment in that context, that should be an error. Even though you could still execute the query, but no data would come out of it. So you have all of these kind of corner cases where it's actually wrong, but in principle and theoretically, it ought to work. Again, the type check and validator steps are not on the critical path, so the speed doesn't matter here as well. The only place where the speed matters is in the execution path that actually runs the query. And the way it does that on the server side is that you have these For each field in the graph that you request, you have a resolver function that you attach to that field that says, how do I render that particular field? And you remember, through the hierarchy of things, you know where your cursor are, so to speak. You know your current object and what field you are requesting inside the object. And there's default resolvers that just picks things inside the objects that you're currently sitting with. So you don't have to supply resolvers for all fields. You only have to supply resolvers for those fields that are working as the default case. And that's usually very few. So of all the fields I showed you here, there's like 2 or 3 resolvers, and everything else is happening automatically. Resolvers can be backed by any code you run. That is, honest to God, standard Erlang code that is just running. So you can do anything in a resolver you want. And this is how you implement, say, mutations, because now your resolver is just going to the database and adding data. There's a lot of things I didn't cover. I didn't cover all of this, so just know that there's a story inside GraphQL for doing these things. So subscription, streaming of events, all of that kind of stuff is inside there. There's a story for doing authentication, authorization through this. There's a lot about error handling that I didn't show that is also part of this system, so you can actually get error handling. There's a lot of things about how do you, so GraphQL is very broad, but then what they do in, say, Relay and React is that they say, let us define certain standard ways of doing certain things. So let us define a standard way of doing, say, pagination. Let us define a standard way of introducing a new object into the graph. And then utilize this by doing it through a standard, then these libraries gets much more powerful because they can assume a lot of things are present in the graph. There's an internal schema validator that verifies that the schema is actually type-wise consistent internally. There's a concept called directives, and you can alias field names if you want, which I didn't show. Note that the standard is pretty fast evolving, so I cannot really keep up with all the things that they're adding right now. So the last draft spec is from April this year, and I think that we are pretty close to the next one. But the way it works is that internally they toy with new things, and if they like the thing, it goes into the draft, spec. And then the Erlang implementation I have is about 80% done, something like that, 90% done. So I don't have, say, directives yet, but we haven't really had a need for them yet. That's essentially it. If you want to try it, there are other server implementations. At least I know about JavaScript, Elixir, and Python. That's that part. In the client implementations, I'm only familiar with the React Relay way of doing things, but I'm pretty sure that, I mean, you can write them in any language you want. It's pretty easy to make these queries. So essentially, you can pick your poison. But I don't know what you want to pick. Yes, and now we are reaching questions. Sure. I've unfortunately not. Oh, it's a Microsoft thing, right?
Well, it's one of those Microsoft open standards. But
Yes. So I kind of grasp what OData is, but I haven't really worked with it, and that makes it hard because I cannot really say how it is in relation to this. My experience is, in comparison to standard Restful frameworks, this seems much more powerful. There is an other alternative to this, which is kind of simpler, which is the one Netflix is writing, which is called Falcor. So that is another standard that works a bit like this. The general trend looks like we are going in this direction, where the clients are doing queries to the servers, and the servers are trying their best to respond back to the clients. So you see OData is perhaps, it's a couple of years old, so I guess that that was the first attempt It might not be good enough, so it might kind of fall off. But then these things are tried, right? But definitely my intuition is that the trend is we're moving in this direction and away from a RESTful backend, at least on larger systems. You also have the CQRS stuff going on, and this fits. CQRS fits very well into this graph language because the query part, and the mutation is the events in CQRS. So that is one of the things you can say about that. Yes. Yes. I don't think that they have a story for this yet. But if this takes off, they need to have a story for this. They need to have a way to handle it. You don't need a lot. I mean, you can do this yourself. What Relay and React adds on top of it is a way that makes it easier to link the objects you have inside your React system to these queries. So for instance, suppose you change an object here. So say you are Facebook and you're liking a story for something. Now there's a story count, a like count on that, right? So how many likes does this story has? So over here we have the story, and now we are adding a like to it. So what the interface wants is to bump the like counter by 1, right? So that means when I do a like, another object changes in the graph. And what Relay and React has are ways to do this automatically. So it knows that once I do a like, I should automatically refresh the story and the like count there as well, right? Because now that bumped. And they're actually even cleverer, because what they do is they do the like, then they bump the counter optimistically in the client, so it looks like it's like this, right? And then when the query actually comes back from Facebook, if it matches what they expected, they can just continue as if nothing happened, right? If it doesn't match, they'll just do a transition on the client that shows you that that like didn't went through, right? So this is how they do it. And there's a lot of this built into React and Relay. So Pagination is a really good example of that, where they have these stories for if I add a new object into a paginated thing, where should it be added, and how can I avoid refetching the whole pagination thing, right? How can I get away with just refreshing that particular object I just added, right? And those are some of the things that React has, and you could do that in Angular as well, but you would have to build it yourself, or somebody else would have to build it. Right?
No other questions? Let's give Jesper a hand.